So we've looked at ionic bonding. We've looked at it from the perspective of Lewis structure, okay? So we saw the transfer of electrons, the forming of ions. We've talked about the energy of those ions coming together to form our ionic bond. It is an electrostatic attraction between those ions. We examined the Born-Haber cycle and looked at the energies of it. We're ready to start, this is a long series of lessons, really many lessons. As we start looking at covalent bonding, we're going to, of course, look at covalent bonding from a lot of different perspectives, starting with using Lewis theory. So, covalent bonding using these Lewis structures. What is a covalent bond? A covalent bond is nothing more than an attractive force formed by the sharing of two electrons between two atoms. As soon as these two atoms are sharing those electrons, it puts them in proximity to each other. It's an attractive force from that. So that's what a covalent bond is, a sharing of two electrons between two atoms. Now, once you have a compound that has nothing but these covalent bonds in them, then that compound is called a covalent compound. Some of our covalent compounds are molecular compounds, so we used that term earlier to represent our covalent compounds. It's kind of interchangeable, but not exactly, and we'll see the subtle difference as we proceed. But if you have nothing but covalent bonds, you've got a covalent compound. Here is a way that we represent a covalent compound or a covalent bond, either way, using a Lewis structure. So we use our Lewis symbols. So we have hydrogen on the left. Forget that big dot on the left. That's my bullet point. But there's a little dot on the right. That is the valence electron of hydrogen. And then we've got another hydrogen with its one little dot, its valence electron. So each of these hydrogens have one electron apiece. But the nearest noble gas is helium, and helium has 2 electrons. And so this hydrogen is not happy, this hydrogen is not happy. But if they could get close enough together to where they could put their 2 electrons in and share those 2 electrons, then that would make a happy hydrogen. So here we've got our hydrogen sharing electrons. We can share those electrons and represent them as 2 dots, as we see in the image there. So this is a representation of the sharing of 2 electrons, where this hydrogen now thinks that, hey, I've got 2 electrons, okay? And this hydrogen says, hey, I've got 2 electrons. So that's one way that you can show a sharing. You can also show a sharing with a line. Okay, it's easier to draw a line, in my opinion, than 2 dots. So that is another way of showing the sharing of 2 electrons. Okay, now when you draw these Lewis symbols, you only and always only use valence electrons. So you'll have to count up valence electrons, and you'll have to decide how are they going to share in order for everybody to have 8 valence electrons. Now, I'm not going to teach you the rules of this yet. We're just going to look at the properties and the things that we can learn based upon the Lewis structures. Okay? So we'll only use valence electrons. So here is another example. We've got fluorine. Now if we go to a periodic table and look at fluorine, fluorine is in the 7A family, so it has 7 valence electrons. So we see 7 dots drawn around each of those fluorines. Now we know that that is not a happy state. A happy state is being like the noble gas next to it, which is 8. Now, one fluorine is not going to say, well, all right, you can have my electron, I'll give it to you, and I'll be positively charged and you be negatively charged. There's no way fluorine is going to do that, because fluorine also wants an electron. So we don't have, and let's not scribble it out, let's erase. We don't have ionic bond. What we do is bring those guys close enough together so that they can share. Now we see that each fluorine is going to have valence electrons and have 8. So let's forget about that little for just a minute. So this fluorine says, hey, I've got 8 electrons because I've got those 2 I'm sharing plus the other 6 I have. This one says, hey, I have 8 electrons. The 6 that I have plus the 2 I'm sharing, that's 8. Same thing is being represented down here. Remember, those 2 electrons are written as just a line, so either way we look at it would be that. So now let's also look at some other definitions here. Erase that for just a moment, and let's think about what a lone pair is. A lone pair is a pair of electrons that are not involved in a covalent bond. They are still valence electrons. Now, fluorine had 7, so they're still valence electrons. They're being represented in our structure, but they're not involved in bonding. So here is a lone pair that we see right there. That would be a set of electrons. All right? Let me erase that because it's going to show up on my next thing that I've got up here. The whole thing that we see here is a Lewis structure. So a Lewis structure is going to show the covalent bonding. It'll show bonding pairs. And it will show the lone pairs that we have just defined. So where are bonding pairs? The bonding pairs are the shared pairs. So we call them bonding pairs because they are being shared. They are the electrons that make the bond of the atom. Okay, so we've already talked about this, but we'll go ahead and get it in our notes. Why do the fluorine atoms share their electrons in this way? Well, it's called the octet rule. The octet rule says that atoms other than hydrogen, okay, hydrogen doesn't do this, tend to form bonds until it is surrounded by 8 valence electrons. Now, this is the octet rule. It is not the octet law. It is not a law, but it is a tendency. They tend to form bonds until they're surrounded by 8 valence electrons. Now, the question is, how many electrons does each atom have around it in my diagram that we have right here? All right, so we have fluorine, and we've already mentioned this one. He has 8, okay? He's like the nearest noble gas, which is neon. He has 8. So they each have 8 valence electrons, and that is making fluorine the happy guy. All right, so I've got other circles showing up on the screen there. Now, well, we'll talk about that later. Okay, more about Lewis structures. Okay, there it is. Why is hydrogen left out? Okay, if you were to look at a periodic table, and I want you to take time to look at one. What is the nearest noble gas to hydrogen? How many valence electrons does that guy have? The nearest noble gas is helium, and helium only has 2 electrons. So anytime hydrogen is going to do some sharing, he's always going to do sharing only to the level of having a bond and getting to 2 valence electrons. So that hydrogen is pleased as punch to be like that. He doesn't want 8 valence electrons because his role model is the helium with its 2 electrons. Okay? Now, there are different types of covalent bonds. This is called a single bond. So the single bond is 2 atoms held together by 2 electrons. They're sharing those one pair. One pair being shared between 2 atoms is called a single bond. But there are times where 2 atoms are going to share 2 pair. And if they're sharing 2 pair, that would be 2 bonds, and we call that a double bond. And there are times where you have 2 atoms sharing 3 pair, and we'd call that a triple bond. So I want to show you some examples of that. We'll draw them out on the screen. Now, right now, I don't expect you to be able to draw this. I'm just going to show you what they look like. Carbon is in the middle. The oxygen is on either side. Carbon has 4 valence electrons, so he needs to share more in order to get up to 8. So he shares to this extent and gets a double bond. Oxygen had 6 valence electrons. Doing this sharing gets it up to 8. So let's look at here. Does oxygen have 8 valence electrons as it's written now? It was 6, but now he's got, and we'll draw them in, 1, 2, 3, 4, and he's going to claim these 5, 6, and these 7, 8. So oxygen is content with a Lewis structure like that. This oxygen is the same way. Our carbon, which had only 4, now does all this sharing. He has 2, 4, 6, 8 electrons. So that is what we call a double bond. How many electrons are in a double bond? 4. That right there is also a double bond. And this is a way to take the electrons that carbon and oxygen has in order to make them all have the octet rule apply. They have a total of 8 each. Now let's look at an example with nitrogen, N2. So we have 2 atoms of nitrogen connected to each other. If we look at nitrogen on the periodic table, nitrogen only has 5 valence electrons. He wants 8, okay? So we can take the 5 electrons that each nitrogen has, and if we form a triple bond, okay, they both had 5. This uses 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay? So it uses all 10 of them, and it makes both nitrogens happy. So this nitrogen has these 2 electrons plus claims all of these, 2, 4, 6 more. So nitrogen sees himself as having 8 electrons. Happy. Octet rule being satisfied. This nitrogen also takes claim to those electrons. So this nitrogen is also happy. So we can sometimes have to share a whole lot in order to make the atoms obey the octet rule. So this right here is called a triple bond. Okay? We have our triple bond, which is a sharing of 3 pair or a total of 6 electrons. Now, what we need to know once we can recognize the double bond when we see it, recognize the single bond when we see it, recognize the triple bond when we see it, is that the molecules are a little bit different when we get down and look at the molecules themselves based upon what number of bonds they have. So let's look at what defines a bond length. A bond length is the distance between one nucleus and another nucleus. It's not how much distance separates the 2 atoms because they are bumped right up next to each other as we see in this picture here. So the distance between one nuclei and another nuclei, so if I put a nucleus here and a nucleus here and I measured how far apart they were, that's a bond length. Okay, so we see a whole series of diatomic molecules on our screen. We have F2 at the top all the way down to I2, and they are bumped right up next to each other, but the bond length is from nucleus to nucleus, from nucleus to nucleus, and we see the bond lengths changing here. So that's the definition of bond length. Now, all of these examples that I have over here are single bonds. If we did the Lewis structure of all of these, they are single bonds. And they are getting longer in bond length simply because the atoms are getting bigger. But this statement right here, we need to make sure we commit to memory. Bond length always gets shorter as the number of bonds between the atoms increases. Bonds always get shorter as the number of bonds between them increases. So let's go back to our screen here and let's look at the examples that I have on the screen. I have a single bond, I have double bonds, and I have triple bonds. Okay? Now this is a very small atom, so I'm not sure if it would qualify. But I could think of a single bond maybe between, let's see, what if I had a single bond between a chlorine atom and another chlorine atom? Okay? Here is the Lewis structure of this guy. So that's a single bond, that's a double bond, and that's a triple bond. And I'm going to ask you which one is going to be the shorter one. Well, the shorter one would be the one that's sharing the most. So this is shorter. Now we can only make a true comparison if we were comparing a nitrogen-nitrogen double bond to a nitrogen-nitrogen triple bond, or a nitrogen-nitrogen single bond, because the atoms themselves, as we see on the screen, they play a role as well. But triple bonds tend to be much shorter than double bonds, and then double bonds are shorter than single bonds. So that is, for students, kind of hard to grasp at first, because you think, okay, I have 6 electrons in here. Surely that would get really far apart to make room for all those 6 electrons. But we draw them as if they are between the 2 atoms like this, but in reality, they're not being, they're not sitting there holding hands. They're not all sitting between the 2 nuclei. They're being shared, and those electrons are actually encompassing both atoms. And the more you share, the more you get drawn close together. Okay? So triple bonds are the shortest, then double bonds, and then single bonds, as we see here. Okay, so what do I want you to take away from this lesson? Number 1, a covalent bond is shown by a line or a couple dots between atoms. A covalent bond means we have a sharing of electrons. This would be considered a single bond. This would be considered a double bond. This would be a triple bond, depending upon the level of sharing. Why do they share? They share to try to get the octet rule satisfied. Tends to form bonds in order to give each atom 8 valence electrons, which we have right here. And then the last thing that we learned about Lewis structures when we have drawn them is that we can make a judgment about the bond length based upon how many electrons are being shared. The more that are being shared, the shorter the bond.